campus open until everything we can to keep the campus open until November 19th. That's the magic spot. Just to reiterate, I've been saying it twice in every class. I'll probably say it more, but October 19th, there's going to be class. It was formerly fall day. And then November 20th, there will not be class. That's the Friday before Thanksgiving break. So you get one more day on that. And Tuesday, Wednesday, or Thursday, the 17th, 18th, and 19th of November, we'll make an appointment. I'm doing that in all my classes. So there will likely be several people taking their final in any given time slot. But I'll work with you on that. Try to stay healthy. Try to stay healthy. Really, really, really try to stay healthy. So, chain rules. Now, this is another case where the book has one way, and I have another way of thinking about it. It's very simple. They're down there. But the idea of the chain rule is this. I don't know if you've ever even thought of this, but chain rule is what you do to differentiate a function of a function. If you got one function plugged into another, right? So it's used to differentiate that. And so there are two rates of change really involved. Now, if you think about this, suppose, for example, I mean, hypothetically, you see the guy on TV jogging across the top of the train, you know how it's going, right? You know, some kind of Bond, James Bond thing or something. And so that individual is jogging with respect to the train, and he or she is speeding up, slowing down. So there's a rate of change of that person with respect to the train, but there's a rate of change of that train with respect to the ground. So if the person is jogging along and jogs twice as fast, his or her speed or velocity with respect to the ground will double. Right? Then, if, for example, he decides to go twice as fast and the train decides to triple its speed, then it's 6 times with respect to the ground. It's not 5, it's not 3 plus 2, it's 3 times 2. Right? So if the train speeds up 3 times as fast as what it was, and the person is jogging twice as fast as they were across the top of the train, it's 6 times as fast between the individual and the ground. That's the chain rule. So you multiply rates, those speeds. That's the idea. And now you remember, for a function of just 2 variables, if you had f of g of x d dx is what? F g of x times, you got the f prime, so that's the rate of change of the person with respect to the train, times g prime of x. And that's the rate of change of the train with respect to the ground. And you multiply. All right? I don't know if that's the best analogy of explaining a train rule, but I got James Bond into a calculus lecture, so that's worth it. So what I want to show here is the book version, Miller version. I don't see any point in putting the variable there twice. Right? So I do it this way. All right? Where if you have W, say, depends on 2 variables, right? And then each of them depend on time, right? What you do, I have dW dx. This is how fast the person is running with respect to the train. And then how fast the train is running with respect to the ground, all right? And you multiply along that path. And that's why you get this. You multiply it along that path. And then you add the rate of change. W also depends on another variable, y. I don't know what that would be, but it is possible for something to depend on more than one variable. In fact, most things in life depend on probably infinitely many variables. We don't get that philosophic. But you would multiply along this path. And then you add those rates together. And if there were another one, X, Y, Z, I already got W. How about if I put Z here then? Right? I could equally well do partial W respect to Z, partial Z respect to T, and I would add that on here. You don't have to add that on your paper if you don't want to. But however many variables W depends on, you just keep adding them like that, but you multiply along the path. That's the concept. And so to me, it's more intuitive, just to me, that if you take a look at everything W depends on, you have these. Now, it's not inconceivable. I don't mean to sound like Princess Bride, right? Inconceivable. I don't think that word means what you think it means. It's not inconceivable in real life for, say, Z to depend on two other ones, variables, M and N, right? And between M and N, they depend on T. That could happen. What would you do? Same thing. Every possible path to get down to T, you multiply along. So you'd have 4 terms up there. So, this generalizes really nice, but we're just doing this. Now, the book has it where the T's are, and you do each path and multiply along the path. So, anyway. This one is kind of, now, interesting. In the end here, W ultimately depends on the one variable T. And even that doesn't have to be. There's no reason why X and Y can't depend on S and T together. And that happens. And in fact, we're going to get to that. Nothing here. I love my notes a lot. We're going to have some fun in it. So here we have X or Z depends on X and Y, and X and Y depend on T. Okay? X and Y depend on T. So find dz dt. Well, the first thing is dz dt. Oh, I should mention, notice this is dw dt, and you only put the partial symbol when you're taking a derivative of a function that depends on more than one variable. So w depends on x and y, so you have the partial symbol with the w. Right? X and y depend just on t. So that's dx dt. See how that works? You don't use the partial. The partial implies that that variable depends on more than the variable with respect to which you differentiate. So dz dt is going to equal what? Partial z respect to x times dx dt plus partial z respect to y dy dt. What is the partial of z with respect to x? It's going to get long here. Partial of z with respect to x. Product rule. Somebody on the last test, I think it was in this class, I'm pretty sure. We took the derivative of a product by taking the product of the derivatives. So here you have two things multiplied together depend on x. Its derivative is not the derivative of x, 1, don't write this. the derivative of that with respect to x is y e to the xy. That's not the derivative. The derivative of a product is not the product of derivatives. I forgot who did that. That's fine. Probably better. Don't mean to bust anybody's boxes. Right? What you're going to do is the product rule. First times the derivative of the second with respect to x. So it's going to be x. The derivative of that with respect to x is y e to the xy. Right? Plus second times the derivative of the first is e to the xy. That times the derivative of x with respect to t. I go up here, the derivative of x with respect to t is 2t. It's going to get messy. I told you. A second. Partial of z with respect to y. Okay, pop quiz. Partial of z with respect to y, just put it on your paper. No product rule necessary. Because this x with respect to y is a constant. So you just bring the derivative of the top, which is an x down here, gives you an x squared, times partial y with respect to t. The derivative of this is 1 over t. T to the minus 1 is going to be minus 1 times t to the minus 2. That's going to be times minus 1 over t squared. Unfortunately, you don't leave it that way. I'm going to do some simplifying for reasons you're going to see in a second. Right? So this is going to be this first term here. You have e to the xy that can come out front. And then I have a minus. I'm just going to put that the way it is. You know what? Oh dear. That e to the xy could also come off of that. So here's what I'm going to do. This is going to save you some writing in this step here. Because now look at all the variables we have. You have x's and y's and t's. What you got to do is substitute in what x and y equal in terms of t. Okay? So, you see you have x, y together here. So this is going to be e to the x, xy, t squared times t to the minus 1 plus 1, 2t, minus x squared is t to the 4th over t squared. Close bracket. So this is going to be t plus 1. That's going to be t squared. Oh, yeah, sorry. This is e to the xy out here. Why did I do that? This is supposed to be right here. T squared times t to the minus 1 instead of xy. We see that as just a t. Let me pause for a second and let people catch up. All right. So that's just going to be an e to the t bracket. Now watch. 2t times t is t squared, minus this t squared is just a 1t squared. And then 2 to the 2t times 1. That boiled down kind of nice. And the idea is, by taking a derivative with respect to t, you can plug in any time t and get its how fast it's moving or its rate of change. Right? You don't want x's and y's left in there. And you'll find problems in the book of that, even back in 1984. That's interesting, 1984. That's the George Orwell. Any questions? Yeah. Encore solution, right? In this case, it happens to be short. So z is x e to the xy. Just plug in what x and y equal from the beginning. So I plugged in for x and y. Well, that is really easy to differentiate with respect to t. That's a product rule, right? First times the derivative of the second, plus second times the derivative of the first.
That was easy.
This was easy, but my point of doing it the other way was to show you the process of a chain rule. We didn't really use the multivariate chain rule here at all. We plugged in for what the variables equal and took a derivative with respect to t. But you know from related rates and stuff that always doesn't work that way, right? Put it this way, it always isn't possible or convenient to do that. Right? Okay. The radius of a right circular cone is increasing at the rate of 2 inches per minute. Its height is increasing at 3 inches per minute. How fast is the volume changing when the radius is 5 inches and the height is 6 inches? No, related rates, remember that? In this book, they're all the way back in chapter 2 for some reason. I don't know why they're not in chapter 3. Chapter 3 is applications of the derivative. So, you have a little cone here. Like my cone? I think you did a pretty good job making that. I made that in the software here. I'm very proud of myself. Right? So make a cone, and you ask yourself in these problems, it's a 4-step process. 4-step. Step 1. You put down what you're given and what you seek. Given. All right? Now here's the case, the volume depends on the height and radius, right? And if those are changing, the change in the volume depends on two variables, right? So you got V over here. V is connected to R and to H, and they're both connected to T. So that's like our drawing on the other page. That's what they say teaching's about. You got to connect to prior learning, right? So this is that drawing we did. So now we're given what in terms of our drawing over there? The radius is increasing at the rate of 2 inches per minute. That's d. R dt is 2 inches per minute. You're told that dh dt is 3. That's given. And part of step 1 also, what do you seek? You identify from the problem how fast is the volume changing when the radius is 5 and the height is 6. So it's dv dt evaluated when radius is 5, height is 6. Step 2. You find step 2, you find a relationship between the variable whose rate you seek and the variable or variables whose rates you have. So the obvious one here is the volume formula. The volume of a cone, you remember the rule? Anything that comes to a point, you would treat, so anything that goes straight up is the area of the base times the height. If it goes uniformly to a point, it's base times height divided by 3. And that's true no matter where you put the point. If it goes up to a point even way over here, as long as the height stays the same, that volume still works. It's kind of cool. So step 2, you identify that formula. Okay. Step 3. Right. You differentiate this with respect to t. Now, bearing in mind that v is a function of t, r is a function of t, and h is a function of t. Yeah. So we need a little bit of product rule action over here. So this is going to be dv dt equal pi over 3, just along for the ride. Product rule time here. But you got to remember how implicit differentiation works. R squared is first times the derivative of the second. R squared times the derivative of h. So it's going to be r squared. The derivative of h is not 1. The derivative of h with respect to h is 1. The derivative of h with respect to t is dh dt. That's first times the derivative of the second. Second times the derivative of the first, it's a little bit tricky. So you do second, h, and believe it or not, you got to do the chain rule on r. You gotta do the chain rule on R. Because think of it this way. R depends on T, right? If R depended on R, it'd be 2R. But R depends on T. So think of R d R dt, or let's do this one, sorry. D dt of R of T. Think of the chain rule, right? So you're going to have, actually, I'm going to erase that, sorry. So this is going to be, the derivative of R is squared is going to be 2R times the derivative of R with respect to T. This is a common point of failure here, where you have to do the product rule. And every time you differentiate anything with respect to T, except T, you're going to get a d whatever dt come out. You differentiate volume with respect to T, it produces a dv dt. You differentiate radius with respect to T, it produces dr dt. And maybe some r's. Like here, you had 2r from the 2 coming down, 2 times r, and then dr dt. The same with h. Cool part of this, we're ready for step 4. You've been looking forward to step 4. dv dt equals, when r is 5, h is 6. It's going to be pi over 3. R squared is 5 squared dh dt. dh dt. Is 3. I guess so. Plus h is 6. I should have brought the 2 up front, but 2 times r is 5. dr dt is 2. All right. So this is going to be 75 right there. And 6 times 5 is 30, times 4 is 120. So that equals 195 pi over 3. And that simplifies. Because 195 is divisible by 3. So 195 by 3 is 65. Inches cubed for, I think it's a minute. Cool. All right, so these 4 steps, by the way, these are in the book, but they're in the book in section, I think it's 2.6. 2.6 seems like 2nd grade, right? Yeah, 2.6. In section 2.6, they have these same 4 steps for ordinary related rates that aren't ordinary rate. But it's a great framework because it helps you structure your thinking. It structures your approach. Step 1 and building the diagram, they go together. Okay, because to get what you're given, it doesn't give you variable names up here. It tells you radius, height, volume, right? It doesn't give you what you're going to use for those. So you go over here, you make yourself whatever shape you need, and you give them labels, R and H. You can do it X and Y if you wanted to. Then your volume what you're seeking is the volume, how fast it's changing when R is this and H is that. So that tells you what you're after. But sometimes you can get so muddled in this. Related rates are easy to get muddled in. I don't know if I told you, but I've seen very good mathematicians and myself get muddled, but mathematicians much better than me get muddled in basic related rates. They are the bane of Calc 1 students, along with epsilon delta. And she's shaking her head. Did you ever get related rates in your class? But this gives some structure to it, and that's good. And I use this structure myself, and I knew how to do related rates before I used this book. Ostensibly, I knew how to do it. All right? So this just charts out where you're going to go. What you're given, what you seek. You need a formula that connects the variable whose rate you seek with the variable whose rates you have. Right? You differentiate that formula with respect to t all the way across. You get this, you got to use the product rule on that. Then, step 4, you plug in your values. At that point, you should have your values. Once in a while, you got to go back over here and derive a value, right? You know, when the radius is, I could rearrange this problem. When the radius is this, what is the volume? Well, you can figure that out. You can figure that out, right? We are not going to have time for this. Not today. Not today. No, that's what you wanted to hear. That's okay. It's Friday.
Can I look like this?
Yeah, sure. Let me shut off the recording.